Okay, so let's start where we left from. So far, what we discussed is if a returned radar signal carries information about the delay or about, let's say, about the range and velocity or Doppler shift information due to a moving target, we want to understand its effect or how this information carries over after demodulator processing and then match filtering processing. Okay, so here what we have is the output of the match filtering evaluated at 0. Okay, and we're looking at its magnitude, and we said that we're going to arrive at this relation. Now, note that if you're using a single match filter, okay, we don't know the range and velocity of the target. So there is going to be a mismatch between our chosen delay and velocity values and the true delay and velocity values. Okay, let's define these mismatch values as velocity mismatch v and delay mismatch tau. Let's understand how the peak or how the value of the match filter will change at origin due to the amount of this mismatch. Okay, so let's understand that. So now I want to write this function basically in terms of my mismatch terms v and tau. Let's do that. So the first thing we're going to do here is we're going to get rid of this minus u terms. So instead of minus u, we're going to first write x. So we're going to get x minus tau 1 and x minus tau 0 here. And here we're going to get actually minus x. Okay, I believe there is a sign error here. This should be e to the minus j 2 pi vx. And we're going to have a dx again. There is going to be also minus here, but because we're looking at the magnitude of the integral, magnitude at origin, that's not important. Okay, so once we have this thing, now we want to express it in terms of tau 1 and tau 0, which is tau variable. To be able to do that, we call x minus tau 0 now a new variable. Okay, let's call it t. If we do that, we're going to get s bar t here. And here we're going to get s bar conjugate t minus tau. Okay, and tau is this delay mismatch variable. And similarly here, we're going to have e to the minus j 2 pi v, instead of x, we're going to get t plus tau 0. Okay, there is again a sign is wrong. This should be t plus tau 0. Because actually this tau 0 term is not important at all, because this function, when we look at this function, this is going to be the term due to tau 0 will be just a complex factor that we can move outside the integral, and we will get rid of it due to the magnitude operation. So we can simply ignore this tau 0 term. Okay, what is left is basically s bar t, s bar conjugate t minus tau, and e to the minus j 2 pi vt. Okay, I realized that I forgot to open my video. Okay, let's continue. So that's what we arrived at. Okay, so this is what we arrived at. Okay, so this function tells us how much my peak at origin changes with the mismatch amount, delay mismatch tau, and velocity mismatch v. Okay, ideally, what do we want? We want that this function, if our mismatch is small, if we're close to the true velocity and delay values, okay, in our match filter parameters, then we want this term to be quite large. Okay, so for tau and v small, we want this term to be large actually. And that's going to give us a good peak, a nice peak at the output of the match filter, and using that peak, we can simply understand that if we see a high peak, we can say that okay, my match filter parameters, V and tau parameter, are close to the correct one. So I can use use those values as my delay and velocity estimate. Okay. Because of this property, we're gonna call this term that's inside the magnitude a new function, which is going to be our basic ambiguity function. Okay, so ambiguity function is nothing but this term. Okay, and remember that we view this term as a function of mismatch amount for both delay and velocity or Doppler shift. Okay, so we're going to call this function x, ambiguity function. For now, we also call it prime. We're going to understand its reason in a few seconds. And it's going to be function of both of these mismatch parameters, tau and v. Okay. And as we said before, if tau and v, if our mismatch is small, if our match filter parameters are close to the true ones, then we want to observe a large value for the ambiguity function. And also, what will be nice on this ambiguity function will be a quick drop after 0. Okay, so we want this function to fall quickly as it goes far away from the origin. Okay, because that means our mismatch values, if our mismatch value is higher than a certain value, we want to see, we don't want to see a peak value, or we don't want to see a large value on the match filter. So we want to see small values. So we want this thing to be small, okay, after origin. So that means actually, ideally, what we want is we want the ambiguity function to be almost like an impulse, okay, both along. So it's going to be two-dimensional impulse. So we want an impulse both along delay mismatch dimension and velocity mismatch dimension. But mathematically, that's not possible. So it's not possible that you can not find an S of t that you will insert here and the result will be an impulse. Okay, that's mathematically not possible. But the good news, so that's the bad news, but the good news is that you can make the main portion of the ambiguity function very close to the impulse, okay? And then you can let to have more other peaks in other parts of the main portion, okay? So you can make an impulse, obtain an impulse for the ambiguity function near origin, and you can let it pop up, let it like get large values at somewhere else. Okay, that's possible. So what I mean by that, let me maybe provide you a demonstration. Like a function like this. Okay, so this is, for example, a sample ambiguity function. Okay, so you can make it very close to an impulse near origin, but you're gonna have like another large portions at other parts in this case. Okay, so you cannot make to have a single impulse in this function. That's not possible. But if you get an impulse here, you're gonna see other large peaks at other locations. Okay, 2D locations. That's a possible ambiguity function, and that's usually what we use, okay, as an ambiguity function. Going back to our discussion. Okay, so we said that we can have something close to an impulse near origin, and we can have other large values at somewhere else. And these actually other large values will cause ambiguities in estimating the distance and velocity. Okay, so in any radar measurement, there are always like range and velocity ambiguities. Okay, for example, if you estimate velocity as a constant, okay, you can add certain values to that constant, and you can say that okay, that's also a possible velocity, or that's also a possible delay. Okay, but we mostly only we always assume that our target has a certain maximum delay, and a certain maximum velocity that we want to analyze, okay, or that we expect. And then based on that, we design our ambiguity function. Okay, so those ambiguities for us should not create any difficulty in estimating the true delay and velocity values. Okay, if we just keep that ambiguities outside the region of interest for the delay and velocity, then that will not be a great difficulty. Okay, so this is, we said this is will be our ambiguity function, and actually we're going to discuss that. We're going to actually measure this ambiguity function, kind of sampled version of this ambiguity function, by using bank of match filters. Okay, so we're going to discuss that. So if you have multiple targets, you need to use bank of match filters as well. Okay, by using, remember that we used a single, we can use a single match filter for a single target. But if you want to detect two peaks, for example, then you need a bank of match filters that are designed to give you both peaks. Okay, and we're going to also discuss the bank of match filters, the relation of bank of match filters with ambiguity function as well. But before that, let's understand our ambiguity function in some more detail. We define the ambiguity function in this form. Okay, we call this term the ambiguity function, but there is a more common definition of ambiguity function that is used. Okay, so this is a more common definition of ambiguity function. So we call this now X function, not without prime, X tau v. So the only difference between this and the earlier version is actually here we didn't have symmetric shifts. Here we have symmetric shifts, okay, on the signal. Tau over 2 and minus tau over 2. That's the only difference. So basically these two functions are very related to each other, and you can obtain the relation between these two definitions if you multiply this S prime definition with e to the j pi v tau. Okay, you're going to get this new ambiguity function definition. Okay, so they're just simply related to each other by a complex exponential. Multiplication with a complex exponential. So you can actually use any of them for both purposes, but we're going to stick to this definition for now because it has nicer properties because of the symmetry between the delays. This will have nicer properties mathematically, so we're going to use this one. Here also, okay, I forgot to say that we said that there's only a complex exponential difference between that, but usually we analyze the ambiguity function by looking mainly its magnitude only. So if you only consider the magnitude of these terms, they are basically the same terms. So in magnitude-wise, they are basically the same function. So you can use any of them. Okay, let's understand some facts about the ambiguity function. That those facts will also help us to get intuition about the ambiguity function as well. Let's, for example, look at the value. Let's start first by looking at the value at origin. What is the value of the ambiguity function at v tau equals 0 and v equals 0? So 0 delay mismatch, 0 velocity mismatch. Okay, if you insert that here, if your tau is 0 and if your v is 0, okay, you're going to get inside this integral s function magnitude square integrated. Okay, and what's that? That's basically the energy of the s bar function. Okay, this is the energy in s bar function. For simplicity, we are now dropping the bar here. So this is the energy in the S bar signal. Remember that S bar was the output of the demodulator system. So it's the complex baseband signal. But remember that match filter always operates after the demodulator. So it always operates on the demodulated signal. So everything we have as signal term in the ambiguity function are the demodulated signal. Okay, so this is S bar T. So at the origin, we have the energy in our actually signal. Okay, and if you look at its slices, let's look at its slice along tau. Okay, we insert v equals 0 to understand the behavior along tau slices. Okay, if we do that, if you insert v equals 0 here, what you're going to get? You're going to get just this term, multiply with this term, and integrate it. And this is a special name. We call this thing autocorrelation function. Okay, this is autocorrelation of the signal. And if you look at the slice along V, okay, by letting tau equal 0, in that case, we're going to get rid of this term. Okay, so we're going to get rid of this term. And what you're going to end up with will be a Fourier transform expression. Okay, so you get rid of this term, tau term. So you just have here the magnitude of S of t, and here there is this term, which is basically taking Fourier transform. So you're going to have Fourier transform of magnitude of S of t. Okay, magnitude square, actually magnitude square of S of t. And that's what you're going to see in the V slice. So what does that mean? If you look at those things together, so suppose this is an ambiguity function. At the origin, you have the energy of S of t. If you look at the slice, this slice along this axis, okay, you see the autocorrelation function of the signal. So it's a time domain signal, what you observe along the slice. But if you look at the slice along V direction, along this axis, what you see is a frequency domain signal. Okay, it's the Fourier transform of the magnitude square of the signal. Okay, so you can think that on this dimension you carry frequency information, and so which is actually what it should be, because V is the frequency variable, right? Mismatch variable, velocity mismatch variable, and tau is the along tau you have the time domain information. Okay, so it's you can think ambiguity function as a time frequency distribution. Okay, so there is a general class of time frequency distributions. Ambiguity function is thought of one example of that. Okay, so let's also discuss some important properties of ambiguity function. If your demodulator output is a delayed signal, okay, the effect of this delay on the ambiguity function will be just modulation of this ambiguity function with this complex exponential, okay? This term. This is actually what you can expect. So this is a complex expansion with respect to V variable. Remember that delay by an amount of delta in time domain causes a frequency shift of delta. Okay? And remember that the frequency content is carried over V axis. So that's actually what you see here. If instead you have frequency shift in time, okay, if you add your signal a frequency of f, then the effect in the ambiguity function will also this frequency f, okay, added to your ambiguity function. So you're going to have modulation with a complex exponential of frequency f, okay. So in time domain, you're gonna for the tau variable, you're gonna get multiplication with this frequency along the tau x. Okay. Another important property. This can be actually even the most important property of the ambiguity function. Scale. If you have a scaled signal at the demodulator output by a scale of a, what we're going to see in the ambiguity function, we're going to have same scaling effect along time variable, because remember that that's actually a time information, it carries time information. So have same scaling with on this for this variable tau, but we have opposite scaling for the variable v. Okay, and remember that this carries frequency information. This carries frequency information. So we see this inverse scaling effect on the v variable, and we also have this 1 over a scaling term in the front. Okay, maybe because of mostly because of this a term here. Okay, so what is the interpretation of this property? If you stretch, if you enlarge your S of t signal, okay, if you have an enlarged signal at the input of the match filter, then it tells you that your ambiguity function will also get enlarged along the delay mismatch dimension, but it's gonna get squeezed in the velocity mismatch dimension. So what will cause that? What will this cause? You're going to have a larger extent along tau dimension, which will tell you that your range resolution will get worse, okay? Because you're going to see large values for the ambiguity function for a larger range of tau values or delay mismatch, and oppositely, you're gonna see better resolution because of this squeezing operation along v dimension. You're gonna get better velocity resolution or Doppler resolution. Okay. So here we also see again the trade-off between range resolution and Doppler resolution. So you cannot make the ambiguity function to be to have like small extent in both directions. If you squeeze it along tau, you're gonna it's gonna get enlarged along the other direction. Okay, so there is this trade-off between these two resolutions. As a third property, if we modulate S of t, if we see as a chirp modulated version of the signal in the input of match filter, then the effect in the ambiguity function will be, there will be actually no effect on the tau axis, but the v axis, we're going to contain now both the delay mismatch and velocity mismatch. So you're going to have v minus alpha tau. So that's a linear linear mapping, linear coordinate mapping operation, linear coordinate transformation for the ambiguity function. Okay, so if you have, for example, if your ambiguity function look like this, suppose these are the curve levels, level sets for this ambiguity function. This is gonna, after this operation, coordinate transformation, you're gonna see this type of shape, okay, for the ambiguity function. Okay, so these are the important properties for the ambiguity function. Now, to actually understand what an ambiguity function means in practice, okay, so you can also we can also look at an infinite bank of match filters. Let's do that. I already told you that the ambiguity function is related to the output of an infinite bank of match filters. We will now understand that. Suppose, again, we have a return signal after quadrature demodulation system, okay? And that return signal arrives us from a point target. Okay? Suppose it's a point target with delay tau 0 and velocity v0. Okay, that means we're gonna receive our return signal will look like this. It's gonna carry the delay information tau 0 and velocity information v0 in this fashion. What will be the match filter output in this case? Okay, so for this case, we discussed the match filter output at the origin t equals 0, and we said that it's going to be this x prime function, ambiguity function, evaluated at tau and v Okay, tau was T1 minus T0, V was V1 minus V0. We want to now go back to, so this was in magnitude, okay, magnitude-wise. Understand this match filtering output in its complex form, okay, complex values form. So we insert back the phase term we dropped before, okay, this was the phase term we dropped before when we were computing the magnitude. Okay, so we remove this, we put this term back. Here, the critical thing is, one of you already mentioned this before. Here, the V is a very small frequency. Okay, it's usually in few hertz, and similarly, the tau. So this is actually the velocity is already a small value, and here V is the velocity mismatch value. So it's even small. It's usually few hertz, and the delay due to the target, which is tau zero. Tau zero is generally few milliseconds. Okay, it's also something very small. So that means in general we're gonna have here a term that's almost one. Okay, so we inserted this phase term back, but actually we realized that we can actually still ignore it because it's usually very close to one. Okay, even in its complex form, y0 is just this x prime ambiguity function. If you write it in terms of tau1 minus tau 0 and v1 minus v0, it's going to look like this. Now we want to understand the output of match filter is a function of time, actually. So so far we were only looking at its value at origin, whether we see a peak at the origin or not. But let's look at the match filter output as a function, time domain signal. Okay, so let's look at YST. To view that actually YST, you can think that your match filter delay parameter tau1 is set to 0. Okay, if you set your tau1 parameter to 0, okay, and yes, if you choose your match filter delay parameter as 0, then you are going to get just minus t0 here, but this is at the origin. But if you view this as a function of t, if you go back to our previous derivation, from there you're going to get this relation. So YST is a function of t. Your match filter output in this case will be just x prime t minus tau 0 and v1 minus v0. Okay, so that's going to be the observed filter output at a general time t. Now, this is still for a single match filter. Okay, our match filter delay parameter is 0, and it has a velocity parameter v1. Now we want to make infinite bank of this match filters. All of them has delay parameter 0, but each has a different velocity parameter v1. Okay, so let's say we have infinite bank of match filters with continuum of v parameters. Okay, so let's say v1 is a continuous parameter, continuous valued parameter v. Okay, in that case, our function, our ambiguity function, our match filters, we can view our match filters now also as a function of their v parameter as well. And it's going to be simply equal to t minus tau 0 and v minus v0. The ambiguity function evaluates at these values. Okay, so this is going to be what we will measure at the output of an infinite bank of match filters. Okay, if you view the output as a two-dimensional function. Here, what was critical up to this point? Our function, our target was a point target. Okay, now, in imaging problems, generally, we're not looking at point targets, right? We look at extended targets, which are larger than a point target. Suppose we're also looking at an extended target with this radar system. So that means, so we have an extended target. So every point on this extended target can have a different distance, okay, can cause a different delay, and can have a different, can cause a different Doppler shift. So we're gonna get different reflection from each point on this extended target. For example, some points on the target will reflect the radar signal with a higher amplitude, and some points will not reflect it that well. Okay, let's call that reflectivity distribution two-dimensional function that describes how well our extended target is reflecting this radar signal is represented by this two-dimensional reflectivity distribution, rho tau 0 v 0. Okay. If that is the case, then what will be the output of our infinite bank of match filters? The output was this thing for a single point target. Okay, if we have infinite amount of point targets, and for each point target we have this amount of reflectivity, okay, factor, then that means we're going to have this reflectivity distribution, multiply this function and integrate it over tau 0 and v0. Okay, that's going to be our received signal. Okay, or that's going to be the output of the match filter, infinite bank of match filter. So the at output of the infinite bank of match filter, we're going to basically see this function as a function that can cause different reflectivity and that can cause different delay and Doppler shifts. Or so it can cause multiple delays and multiple Doppler shifts. Okay, so it's a function of tau 0 and v0, and then we integrate it with respect to tau 0 and v0. That's going to be the overall signal received or obtained at the output of this match filters. Okay, as a result of contributions for each tau 0 and v0, we're going to get this measurement. Okay, for an extended target. And if you look at this thing, this is nothing but a convolution relation. It's the convolution of the ambiguity function, okay, x prime, with the reflectivity distribution of the extended target. Okay, so the reflectivity of the target in Rayleigh and Doppler coordinates will be convolved with the ambiguity function. Okay, and that's going to be what we will see at the output of the infinite bank of match filters. So basically, if you are processing your receipt radar signal using many match filters, each matched to a different velocity, the overall impulse response of your system, radar system, the demodulator plus this infinite bank of match filters, will be the ambiguity function. Okay, so your input signal, the reflectivity distribution of the target, will be convolved with this ambiguity function. So this serves, ambiguity function serves as the overall system's impulse response. And with overall system here, we mean the demodulator system plus the bank of match filters. Okay, so you can interpret this like this. Suppose we have a scene, rho tau v, and we have ambiguity function, which is the impulse response of our system. So the output we're going to obtain will be y. Okay, it's just, suppose the scene looks like this, our ambiguity function looks like this. We're going to see convolution of these two as our output of the match filters. So the main portion of the ambiguity function that is close to an impulse will cause us will enable us to see the scene with a good quality, okay, depending on how close this main portion to an impulse. And we're going to also see the replicas of this image due to these other peaks in our ambiguity function, and which are unavoidable, as I said before. Okay, here we stop here.